Hello everyone. Today I'm going to talk about a type of transistor named HEMT, which is the acronym for High Electron Mobility Transistor. Uh, it brings out some good features compared to other transistors like BJT or MOSFETs. The HEMT has high current driving capability and it can function at a very high frequency from some megahertz to terahertz, so it can be used for microwave or radio wave applications. It has high power handling capability, so we can also use it for power electronics for power conversions, and it shows a very good performance at high temperature. Basically, in terms of transistors, their performance deteriorate dramatically at high temperature. Here we are seeing a very basic structure of HEMT. It consists of three layers, namely barrier, channel, and substrate. The main idea behind this device is a heterojunction. This is the heterojunction. Why are you calling it heterojunction? A heterojunction is a junction between two layers whose band gap is different from each other. Here we have used argon as the barrier layer and gallium nitride as the channel layer. The band gap of aluminium gallium nitride, actually it is not fixed, it can be varied from 3.4 to 6.2 electrovolt. It depends on the composition of aluminium, so we can vary the band gap of aluminium gallium nitride, and the band gap of gallium nitride is 3.4 electrovolt. So what we have done here, we have placed a high band gap material above a low band gap material, so their band gap is different. Why? That is why we are calling it as a heterojunction, not a homojunction. On the other hand, their lattice structure is different too, so the lattice constant of these two material is different, so their lattice constant and band gap both are different. Since their lattice constant is different, a stress is generated at this very heterojunction. Because of this stress, spontaneous and piezoelectric polarization takes place. As a result, we get a lot of free carriers in this thin layer between barrier and channel. This layer is termed as 2-dig or two-dimensional electron gas. This layer is very thin, so we are thinking it as a plane, a two-dimensional plane. That's why we are calling it 2-dig. So electron moves across this thin plate, this thin layer. As a result, the velocity or mobility of electron in this device is very high compared to other transistors. Like in MOSFET, the carriers has to move through the substrate where scattering takes place, which reduces the velocity of electrons. On the other hand, here the barrier layer is lightly doped with N-type dopant, and the GaN layer is undoped, and we have placed the source, gate, and drain above the barrier layer. Actually, this gate and this barrier, it is a Schottky junction, and the source barrier and drain barrier, these are ohmic junctions. Here we can see some basic semiconductor ideas, like in terms of an intrinsic semiconductor, the Fermi level, where the probability of finding electron is very high, almost 50%. In terms of intrinsic semiconductor, the Fermi level lies right at the middle of the band gap between conduction band and valence band. It lies right at the middle point. Okay, the Fermi level plays at the middle point of conduction band and valence band. When it is doped with N-type dopant, so we are having here a N-type semiconductor, the Fermi level it moves above and it comes closer to the conduction band. So what we can see that the Fermi level comes closer to the conduction band. So we can say the probability of finding electron in conduction band has increased compared to this scenario, as the Fermi level is now closer to the conduction band. And here we can see a p-type doped semiconductor. As it is p-type doped, so the probability of finding electron in conduction band has reduced. So the probability of finding electron in valence band, it has increased. So there are a huge number of electrons in valence band, but not in conduction band in p-type semiconductor. But in terms of n-type semiconductor, the probability of finding electron in conduction band is very high. So there are a lot of electrons, free electrons carriers in conduction band in terms of n-type semiconductor. Here we are seeing the band diagram. As we have already said, a stress is formed in this heterojunction as the lattice constant of these two material is not the same. So as a result, and we have also said, we have seen here that the Fermi level for an intrinsic semiconductor and for an n-type semiconductor is not the same. For an intrinsic semiconductor, the Fermi level lies right at the middle of the band gap, and for an n-type semiconductor, it's closer to the conduction band. So here, at this heterojunction, the Fermi level of the barrier, which is n-type doped, its Fermi level is closer to the conduction band, and the Fermi level of gallium nitride, which is undoped, its Fermi level is right at the middle of the band gap. So here we can see this is the heterojunction here. Above this heterojunction, the argon layer, and below the heterojunction, there is the gallium nitride layer. This argon layer is lightly n-type doped. Okay, here we can see the Fermi level for the aluminum gallium nitride at the left hand side. At the left hand side of this junction, the Fermi level of the aluminum gallium nitride, Fermi level for aluminum gallium nitride is close to the conduction band since it is n-type dope. Okay, and for gallium nitride, the Fermi level lies right at the middle of the conduction band and valence band. It's placed at the middle of these two bands. Okay, but for aluminum gallium nitride, it's closer to the conduction band. So what happens? For a device, the Fermi level for different materials can't be different. It has to be same throughout the device. So as a result, the bands, the conduction band and the valence band bends. What we can see here, the conduction band of gallium nitride, this is the heterojunction. At the right side, this is gallium nitride. At the left side, this is argon. So the conduction band, this is the conduction band of gallium nitride. The conduction band of gallium nitride bends downward and it falls right below the Fermi level. We can see this conduction band bends and it falls below the Fermi level. So as a result, what happens? Normally it is the tendency of electrons to possess low energy. So as a result, electrons in this GaN layer falls in this trap. Electrons from gallium nitride layer falls in this trap, in this very small trap. So what we get a huge number of electrons in this very small place. The concentration of electron is very high here. From where the electrons are coming? They are coming from this gallium nitride layer. It's high energy compared to this line. This trap, this small, what we call a quantum well, energy of this quantum well is comparatively lower. So electrons falls in this trap and they get confined here. They get confined right in this place, what we call a 2-deck that we have said here. So actually this is the quantum well or the trap where electron falls and confined, and this 2-deck is formed throughout this device. Okay, so here the concentration of electron is very high and it's a thin layer, so there is we can say there is no scattering, so the mobility of electron has to be very high. Okay, so this is the main principle behind the working of HEMT. Thank you.